In this lecture, I'm going to talk about the relative strengths of different acids. So a strong acid is one that completely ionizes in water. HCl is a good example. And you can think of this as being very similar to a strong electrolyte. So the ions fully separate and become dissolved in water. This means that there's a bunch of the hydronium ion, or that H3O+, which you can use as H+ as a shorthand, and the chloride ions. A weak acid, on the other hand, has incomplete ionization. So HF, which is also hydrofluoric acid, you would find some of the hydronium ion, some of the fluoride anion, but also plenty of the intact acid. With a strong acid, we tend to use single arrows to indicate complete ionization. Now, I understand that that is a little difficult sometimes with the computer, and so I'll do what I can, and you can also do what you can. I'm not going to penalize you if you can't use this equilibrium arrow, but at least in the textbook and in most of your homework, it should have that equilibrium arrow to indicate partial ionization. So if you ever see an acid and the equation is set up like this with an arrow in a textbook, or the arrow is like this, you know right off the bat if it's a strong or a weak acid, because the strong acid essentially goes to completion. There's no reversibility here, but with the weak acid, this is an equilibrium reaction because you have an equilibrium between the weak acid and its conjugate base form in water. So we measure acid strength by the acid ionization constant, Ka. So what this is the equilibrium constant. So this is much like the Kc that we talked about with the last chapter. This is the acid ionization constant. And so we could write an equilibrium expression for this equation, and it would look like this. Remember, we do not use pure liquids or solids that are in excess in those equilibrium expressions because the concentration is so much greater. So with our Ka expression, we would have our H3O+, hydronium ion, or the H+, the proton, and the conjugate base, the A-, which we have here, and then in the denominator, we have our intact acid. Now, if this were a strong acid, there would really be no HA, it would be almost zero, so this would be kind of meaningless. But for a weak acid, where you have values for all three of these, that Ka will be a number that will give you a lot of information. If K is much less than 1, that means that the concentration of products is low and the concentration of reactants is high, and so the reverse reaction would be favored. If K is much greater than 1, the forward reaction is favored because the concentration of the reactants would be very low and the products would be very high, right? So if the denominator is large and the numerator is small, you get a small number. And that is true when you have a weak acid. When you have the large number on the numerator, then you favor the products, and that is true for strong acids. So let's look at these K values and rank them in the order of acid strength. So this HBr, we have our Ka 1 times 10 to the minus 9th. So we know that this is the largest K. Then we look at this guy here. This is hypochloric acid, and it's 2.9 times 10 to the minus 8th, quite a bit lower than this one. And then HF, hydrofluoric acid, our Ka is 3.5 times 10 to the minus 4th. So this is the largest K value, so it must be the strongest. This has the smallest K value, so it must be the weakest, and HF must be in the middle. If you're having trouble remembering this, look at the equilibrium expression and remember where it comes from. Your Ka will be very, very small if the big number is on the bottom. So the smaller it is, the more intact acid you have. So let's think about why that is. Like, what is the chemistry behind this? So I've told you that we call HCl a stronger acid than HF because it fully ionizes in water and this one doesn't. But what is the chemistry that explains this behavior? I want to just remind you really quickly that I'm using the Arrhenius acid definition, where it produces protons when dissolved in water. And so with my strong acid, there's a weak attraction between the conjugate base and that proton. The H plus is not very tightly bound to its conjugate base. Like, this is a weak interaction. And so it's very easy for this to completely ionize. With a weak acid, there's a stronger attraction. So there's only partial ionization. So the more difficult it is for the conjugate base to let go of the proton, to let go of the H plus, the weaker the acid is. So let's look at some binary acids. Remember, binary acids have just an H and then one other thing. And so the stronger the acid, the easier it is to remove the H plus. If we had HLI, we would see that is not an acidic compound. HC, not acidic. So you might hear me say things like acidic proton. This is an example of an acidic proton. It is a proton, it is an H that can participate in an acid-base reaction, whereas these cannot. So for example, methane, CH4, none of those H's are dissolved and are released as protons in acid-base reactions. So we would say they are not acidic. And so we can look at electronegativity and see that the more electronegative the compound is that the hydrogen is bound to, the more acidic the compound is going to be. These are too difficult to remove to even function as acids. However, fluorine is so electronegative, it pulls most of the electrons towards itself, so that H is really vulnerable for attack by other compounds that want that H. And so the hydrogen and the fluorine dissociate. We can also look at decreasing bond strength. And so the bond energy of HF, 565 kilojoules per mole, it's the weaker acid. HCl, 431, HBr, 364. So these get stronger as they go down the periodic table because of the bond energy. And increasing electronegativity also increases the acidity. So we can look at bond lengths. Fluorine is the smallest of the halogens, and so the bond length between an H and an F is going to be much smaller than between an H and a Cl or an H and a Br. And so it makes sense that the HF would be a stronger interaction than HBr, for example. So we can also look at the molecule structure. And so with a binary acid, they just contain H and one other element, so HCl. So you just have to look at the bond polarity and the size of this compound. But what if you're dealing with something that's a little bit more complex, like an oxyacid? Remember, the oxyacids have an H that's bound to oxygen, which is bound to other elements. So this is perchloric acid here. We also had looked at nitric acid and sulfuric acid in the previous lecture. So this hydrogen is bound to this oxygen, which is then bound to something else. So let's take a look at this. What do we notice? A trend in electronegativity. So as the compound gets increasingly less electronegative, the Ka value gets smaller. So that means the more electronegative, the stronger the acid. Why is this? Well, if you think about electronegativity is pulling electrons towards itself, like chlorine, it's going to be the most polarized of the bonds. So chlorine is pulling electrons towards itself. This oxygen feels more positive and is willing to kick away that hydrogen right there. So again, you want to think about this dipole right here. And as this bond gets more and more polar, and that happens because the electronegativity difference is higher, then that creates a more acidic proton. So let's think about which of these protons shown in red is the most acidic. Well, we have this C double bonded to an oxygen and this oxygen here, and this C is only bound to hydrogens. So we have to think about the polarity of this bond in addition to the polarity of this bond. So we already know that OH is a polar bond, but what about the difference in polarity between these other groups? Well, we know that this C double bonded oxygen has this dipole because oxygen is more electronegative than carbon and will be pulling these electrons towards itself. This will create a partial positive charge on this carbon, which will then pull some electrons towards itself here. Whereas this guy here only just has this one dipole. So that means that this proton right here will be the most acidic. So the answer would be A. Let's talk about a practical reason why we want to understand acids and bases. So heartburn and acid reflux. So heartburn occurs if you eat a little too much or you drink a little too much and you just don't feel that great and you have that kind of burning sensation in your chest. However, acid reflux is a disorder that can be quite serious in some people, and I actually have a friend whose father passed away from throat cancer brought on by untreated severe acid reflux disease. So it is kind of an important thing to be monitoring yourself for. Your stomach is lined with cells that produce HCl. The HCl helps to kill bacteria and also functions to create a good environment for digesting food. You have your diaphragm, which is that muscle that controls the opening between your esophagus and your stomach. And your esophagus does not have those specialized cells. So when the lower esophageal sphincter is open, which is what happens if you throw up, for example, then you get this acid reflux where the acid refluxes up into the esophagus. So GERD is the disorder for this. So acid reflux causes this burning heartburn sensation because the acid is actually burning the cells of the esophagus. So how do we stop heartburn? Well, there's a number of ways to do this, but one of the ways is to try and neutralize all of the acid that's in the stomach. And you can take antacids to do that. The other way is to try to control the environment and not let it get too out of balance. So eating smaller meals, making sure you swallow regularly and stay hydrated, not lying down immediately after a meal. And then in addition, taking compounds, certain drugs that inhibit some of the proton pumps that are in your stomach to lower the acidity can also help. So another fun fact about acid-base chemistry is that it is the reason that onions are irritating to your eyes and make you cry when you cut them. So onions have an enzyme that is once it's released, it produces this volatile compound. And so volatile compounds go very, very rapidly from liquid to gas at room temperature. And so there's a reaction. Here's the reaction. So there's the compound, there's the enzymes, you cut into it, and then this reaction happens, and you have this volatile compound right here that goes up and gets into your eye. So what happens is this compound reacts with the water in your eye to make this, which is sulfuric acid. So the vapor hits your eye, reacts with water in your eye to produce sulfuric acid, and your eyes start to burn. And so there are different ways that you could control this by cooling the onion, freezing or storing it in the refrigerator. That can slow down the vaporizing of that compound to get less in your eye. You can cut onions under running water or underwater so that the sulfuric acid forms in the water instead of heading up to your eye and forming in your eye. You could wear your cool lab chemistry goggles or swim goggles, or try and use some other interesting little techniques to try and avoid getting that sulfuric acid into your eye. Sulfuric acid is a strong acid, so it is fully dissociating. And so you don't need very much to change the pH of your tears if you get sulfuric acid in your eye. And in our next couple of lectures, we'll actually start to do some calculations with different acids and bases and look more deeply at the equilibria.